Picture a small spacecraft, Voyager 2, launched in 1977 on a mission that would push the boundaries of human exploration farther than ever before. Built by NASA, Voyager 2 was designed to be both resilient and resourceful, carrying with it the hopes of scientists and dreamers alike. Racing through the emptiness of space, Voyager 2 embarked on a once-in-a-lifetime grand tour of the outer solar system, venturing into the unknown with only the faint signals from Earth to guide it. This rare planetary alignment, a cosmic coincidence that occurs just once every 176 years, allowed Voyager 2 to slingshot from Jupiter to Saturn, Uranus, and Neptune, using the gravity of each planet to propel itself onward, deeper into the solar system. Unlike its twin, Voyager 1, which veered off to study Titan, Voyager 2 pressed on alone, becoming the only probe ever to visit Uranus and Neptune, charting a path no other spacecraft has followed since. For nearly 9 years, it braved the harshness of space, enduring cosmic radiation, freezing temperatures, and the vast silence, sending back images and data that transformed our understanding of the gas giants and their mysterious moons. In January 1986, after nearly 3 billion kilometers, Voyager 2 reached Uranus, offering humanity its very first close-up look at this enigmatic ice giant world, a planet shrouded in mystery and distant blue clouds. What it found was unexpected. Uranus appeared strangely quiet, almost lifeless, its atmosphere calm and featureless, defying scientific expectations and leaving researchers puzzled. The data revealed mysteries that would puzzle scientists for decades, hinting at a planet that broke the rules, its magnetic field tilted and offset, its rings faint and dark, and its moons unlike any seen before. For nearly 40 years, the secrets of Uranus remained locked away in Voyager 2's data, waiting for a new generation of scientists and engineers to uncover them as technology and curiosity advanced. Little did anyone know the answers were there all along, hidden in plain sight, waiting for someone to look closer and finally reveal the mysteries of this distant blue world. When Voyager 2 swept past Uranus in 1986, it offered humanity its very first close-up look at this distant, enigmatic world, a planet that had long been little more than a faint blue dot in our telescopes. What Voyager 2 found was astonishing. Uranus appeared smooth, pale blue-green and eerily calm, with almost no visible features or storms to break the monotony of its atmosphere. But beneath that tranquil exterior, Uranus hides a secret: its extreme tilt. The planet is tipped over on its side, causing bizarre seasons. Each pole spends 42 years bathed in sunlight, followed by 42 years of darkness, a cycle unlike anything else in the solar system. As Voyager 2 drew closer, its instruments detected something unexpected: powerful radiation belts encircling Uranus, second only to Jupiter's in strength, surrounding a planet that, at first glance, seemed almost inactive and lifeless. This discovery was a shock to scientists. Normally, strong radiation belts are fueled by a magnetosphere teeming with plasma, but Uranus's magnetosphere was almost eerily empty, with little plasma to be found. The contradiction was stark and puzzling. Where was all the plasma that should have been feeding these intense radiation belts? Scientists speculated that perhaps the answer lay with Uranus's moons: Miranda, Ariel, Umbriel, Titania, and Oberon, each a unique world in its own right, orbiting in the planet's shadowy realm. Maybe like Jupiter's volcanic Io or Saturn's icy Enceladus, these moons were active, releasing plasma into space and fueling the belts. But Voyager 2's images told a different story. The moons appeared ancient, heavily cratered, and seemingly geologically dead. No signs of eruptions or geysers, no obvious source of plasma. With no clear source of plasma, the empty magnetosphere made sense. Yet, the existence of such strong radiation belts remained a baffling mystery, defying easy explanation. The data left scientists scratching their heads. How could such a quiet, seemingly inactive system generate radiation belts so intense? The mystery deepened with every new piece of information. Voyager 2's brief encounter with Uranus raised more questions than it answered, sparking debates and inspiring new theories that would occupy planetary scientists for decades to come. Uranus, it seemed, was a world of contradictions, a planet that looked peaceful and uneventful, yet harbored invisible forces of immense power. The mystery of Uranus would linger unsolved for nearly 40 years, challenging scientists to look deeper and question what they thought they knew about the outer planets. For decades, Voyager 2's snapshot of Uranus defined our understanding, a planet with a nearly empty magnetosphere and dead moons. Unlike the bustling plasma environments at Jupiter and Saturn, Uranus's magnetic bubble was eerily vacant. The prevailing theory became that Uranus was simply inactive, its moons weren't supplying plasma, so the magnetosphere stayed empty. This view shaped textbooks. Uranus was a quiet, tilted ice giant, a lonely outpost with little to offer. But one glaring contradiction remained: the intense radiation belts. If the magnetosphere was empty, where did all those high-energy electrons come from? The data didn't add up. It was like finding a city with no people, yet bustling with energy. For nearly 40 years, this paradox sat at the heart of Uranian science. The empty magnetosphere and powerful radiation belts refused to fit together. Scientists were left with a mystery that no one could explain. The answer, it turned out, was hidden in the timing of Voyager 2's visit. For nearly 4 decades, Voyager 2's fleeting glimpse of Uranus shaped everything we thought we knew about the mysterious ice giant. Its data became the foundation for textbooks, documentaries, and scientific models, accepted as the definitive portrait of the planet's environment. But in 2024, a team of scientists decided to take a fresh look at the old Voyager data, this time using advanced analytical tools and new techniques that weren't available in the 1980s. What they found was astonishing. Just 2 days before Voyager's historic flyby, Uranus had been blasted by a rare and powerful solar storm, a coronal mass ejection hurtling through the solar system. This massive burst of solar energy slammed into Uranus's magnetosphere, compressing it and squeezing out most of the charged plasma, almost as if the planet's magnetic field had been wrung out like a sponge. Voyager 2, by sheer coincidence, arrived at Uranus at the worst possible moment, right in the aftermath of this cosmic upheaval, capturing a planet in a state that was anything but typical. The empty, depleted magnetosphere Voyager recorded wasn't Uranus's normal state at all. It was a temporary, extraordinary condition caused by the solar storm's impact. When scientists ran computer models, they found that these conditions, where Uranus's magnetosphere is so dramatically altered, occur only about 4% of the time. In other words, our entire understanding of Uranus was based on a 1 in 25 event, a cosmic rarity that most scientists would never expect to witness firsthand. The revelation sent shockwaves through the scientific community. Voyager 2's snapshot of Uranus was, in fact, a cosmic fluke, an extraordinary accident of timing. The planet we thought we knew, icy, mysterious, and quiet, was likely very different most of the time, with a magnetosphere far more dynamic than we ever imagined. Suddenly, the decades-old mystery of Uranus's empty magnetosphere had a simple, elegant explanation, reshaping our understanding of the planet's true nature. The story of Uranus was about to be rewritten, opening the door to new questions and future exploration. In the end, it's a powerful reminder: sometimes, timing is everything, even when you're exploring the farthest reaches of our solar system. The 2024 discovery didn't just explain the empty magnetosphere, it solved the radiation belt mystery, too. The solar storm had acted as a cosmic accelerator, energizing electrons and injecting them into the radiation belts. In one event, the storm both emptied the magnetosphere and supercharged the radiation belts. Voyager 2 hadn't seen a dead system, but one jolted by a rare solar outburst. This changes everything. Uranus is likely far more dynamic than we thought. Its magnetosphere is probably filled with plasma, much like Jupiter and Saturn. The quiet, dormant world we imagined may actually be active and ever-changing. The lesson is clear. A single data point can be misleading. Voyager 2's flyby was just a snapshot, taken during a cosmic blackout. Now scientists must rethink everything about Uranus from the ground up. With the solar storm theory, Uranus transforms from a dull outlier to a dynamic, active world. If its magnetosphere is usually full, something must be supplying plasma, perhaps the planet's atmosphere or its moons. This reopens the question of what's really happening beneath Uranus's blue-green clouds. The planet's strange tilt and cold, featureless appearance may hide complex weather and aurorae. The interaction between a lively magnetosphere and the atmosphere could drive phenomena we've never observed. The moons, too, may play a bigger role than we realized. Science thrives on new perspectives, old data, new questions, and the courage to challenge assumptions. As Voyager scientist Linda Spilker said, this discovery will change our view of Uranus once again. It's a thrilling moment, a lost chapter in planetary science, finally revealed. Uranus, once overlooked, is now one of the most exciting worlds to explore. The new findings force us to reconsider Uranus's moons. If the magnetosphere isn't usually empty, maybe the moons are geologically active after all. Cryovolcanic eruptions could be sending water, ammonia, or methane into space, feeding the plasma environment. Even old Voyager 2 images hinted at strange activity. Miranda's chaotic terrain and Ariel's youthful surface suggest recent geological change. If these moons are ocean worlds, they could be among the best places to search for life beyond Earth. The possibility of hidden oceans and active geology transforms Uranus's moons from dead rocks to tantalizing targets. The search for life in the solar system may have just gained a new frontier. The realization that Voyager 2's view was a cosmic fluke has sparked urgent calls for a new mission. Scientists want a dedicated orbiter to study Uranus and its moons over years, not hours. The 2023 Planetary Science Decadal Survey named a Uranus orbiter and probe as NASA's top new flagship mission. This mission would map the magnetosphere, probe the atmosphere, and search for subsurface oceans with advanced instruments. Launch could come in the early 2030s, with arrival more than a decade later. The scientific payoff would be immense, finally revealing Uranus's true nature. The 2024 discovery adds urgency. We're not just filling gaps but rewriting the story of a world we barely know. The next great journey of exploration is waiting at the edge of our solar system. As of July 4, 2025, Voyager 2 is nearly 21 billion kilometers from Earth, still journeying into interstellar space. Its power is fading, but its legacy endures. Its data continues to reshape our understanding decades later. The Uranus revelation proves that even a single flyby can spark new discoveries long after the mission ends. Voyager 2 is more than a machine. It's a symbol of human curiosity and the drive to explore. Its golden record carries our story into the cosmos, a message to the unknown. The greatest discoveries sometimes come from looking again at what we thought we knew. Voyager 2 reminds us, the universe is full of surprises waiting for us to ask the right questions.